So we want to take a closer look at probability today and really remember that probabilities help us generate the idea of how likely something is to occur so that we can make a decision on whether or not what we're seeing falls in line with that, whether it's significant, and really some of the statistics can actually help us identify some of those probabilities. So they really go kind of in line with one another. So when we think about probability, one of the things that is most common for us to think about is really the idea of that probability is a long-term tendency when we think about that. So if we think about if we go over many trials, the probability is what is the relative frequency that we will eventually approach. It's not a short-term thing, it's a long-term thing. And so let's take a look at coin flips to illustrate this. So if we were to just take a coin toss, and let's say we were going to toss a coin 10 times, and we were just to watch whether or not it lands heads or tails, and we were to ask someone, what is the likelihood that it lands on heads? And if we did that 6 times, we would say that the probability is 60%, right? Or 6 out of 10 times. Now again, if we were to toss it 10 more times, that probability or that likelihood might change. And if we think about maybe tossing this over and over again, we would start to see that the probability or the relative frequency starts to get less and less variable. And if we think about that, now obviously if we think about what is the true probability or the theoretical probability in this case, we would say the theoretical probability is 50%. But probability is about what is going to happen in the long run, not as what is happening with short term, because again, it takes a long time to get to that theoretical probability. So that's not, when we think about our definition of probability, don't think short term, think long term. And so many trials, so hundreds, thousands of trials. And so again, predictability in the short term is very difficult. And that's why we talk about long run probability instead. So another concern that we have with probability is the idea of being due for one, knowing that probability will even itself out over the long run. And this is really a fable. Sometimes they call it the gambler's fallacy, because you think that if a person loses over and over again, that eventually they're going to win, and the probability does not ensure that. So if you look at these two fair coins and you flip them and you look at the first situation and then this last situation where we have this streak of heads, and when you say which situation is more likely, the fact is these situations are equally likely. The probability from one situation is really not different from the other, and though we would say that some people would say that streak of seven heads is not likely to occur, but it's actually equally likely from the situation above it. So again, this is where our intuition isn't always in check with kind of what reality is. So we're going to think of, our simple definition of probability is the idea of what is the number of outcomes that we want to happen out of the total possible, right? And we can only use this simple definition when all of the outcomes are equally likely. We'll talk about what happens when not all outcomes are equally likely, but this is a very simple definition we'll start with. So this is just a real easy example so that we can just get some notation down as well. So when we think about a probability situation like this where we have a jar and we have 20 marbles in here, we're going to say that R is, we're going to abbreviate that as the event, and then the notation, notice we just do P, and we say that we usually say this is P of R. So P of R stands for the probability of event R occurring. Now, if we think about the probability and we think about P of R is the event occurring, so then that would be 8, and then 8 plus 12 is 20, right? So the idea would be that the probability of R occurring is 0.40. Again, this is the long run frequency, not anything in the short term. This is what would happen over many, many, many trials. Okay, now we can change this and we can give that definition as 0.40. We could also we could also communicate it as a percentage. Do one or the other. It does not matter. Even if it asks for a percentage and you give it as a decimal, that would be fine. Okay, now a couple of properties that you want to observe with this is that obviously probabilities are somewhere between the values 0 and 1. We can't have a probability over 100% or over 1. And you can't have anything less than 0. The other thing too is that the probability of all the events that we have in a situation have to add up to 1. So in this case, if we think about the red marbles, the only other event that could happen if you're drawing a marble out is the blue marble. And so theoretically, those two events have to add up to 1 or 100%, and in this case clearly they do, right? So again, these are just some simple probabilities. Now when we think about the complement to a probability, we think of that the probability of something not happening. We're not going to say that it's the opposite because again, sometimes it doesn't necessarily work out notation wise or situation wise to think opposite, but think the event not happening. And so if we have the probability of that, we're going to use a little superscript, we call it, where we put C sort of up where the exponent should go. And so that notation is going to be complement. And again, this is just some basic probability notation that we have here. So if you think of the probability of red, of the complement to red, which would be technically the probability of blue happening, right? So you could actually label it two different ways. A lot of times if there's more than one event, complement means all of those events, so that's why we would want to do that. So this would be another way that you could calculate a probability, like the probability of blue is thinking as it's the complement to red, and we sometimes do this with geometry as well, kind of the geometry models. So a probability model is going to be is where we think of all the possible outcomes and their probabilities. So in order for it to be a complete model, all of the probabilities have to add up to 1, meaning that in a situation like this where we have maybe 4 different types of beads that have collected, and we look at all of those different types, we need to make sure if it's a legitimate probability model, these probabilities, all 1, have to be from 0 to 1, and 2, the probabilities have to add up to 1. So you can see from the probabilities here that these clearly add up to 1. So this would make it what we would say a complete, or sometimes they use the word legitimate probability model. So there's some probabilities here, and what I'd like you to do is I encourage you to pause this and see if you can come up with the probabilities of each of these examples 1 through 4, and then press play and then see if you are correct. So hopefully you've tried each of these, and so if we look at the probability of when we say Q is a red solid bead, so we would think the probability of that is going to be 0.40. Then if we think about the probability of R selecting a red bead, that's actually both of these together, so you would have to say 0.07. Now the complement to Q is going to be anything that is not a red solid bead. So that is going to be all of the other beads here. And then if we think the probability of not having a red bead, then clearly that's going to be a green bead. And again, you could calculate this a couple of different ways. Again, the important is that we show how we're thinking about it as we go through. So we go back, I want to finish with this, and we'll come back to this. I talked about this earlier in the year about the stop and frisk program in New York City, that we was having a disproportionate way of pulling people over, and in this case it was kind of it was even just walking around. But one of the things that was a real problem with it is that the fact that a lot of these stops really didn't occur with any sort of arrest or summons that happened here. So I want to use the idea of probability to think about, okay, so could we come to some sort of observation that might cause us some questions or concerns or things like that. So remember, this was the data that we pulled from 2011, and we looked at this before as the marginal distribution and said here was the percentages of each of the different races that were involved in the stop and frisk in this 2011. So the question would be, if we look at the population of New York City at the time and look at that, could we, if the stops were truly done at random, what should the stops look like, right? And the idea of proportion, we talked about association, right? And we said, okay, so here's if the proportion of stops were the same as the population, here's the percentages of what we should see from each of those race groups, right? And remember what these percentages were, right? Here's the actual percentages. Now you can see that we said then there was some sort of association with this, and when we talk about probability, we think of over the long run, over many stops. What's the proportion of time that a person who is black is going to be stopped, right? Or that the stop will be a person who's black versus a person who's white. And so that, again, when we think of probability, think of over and over and over again with those. And so then, there's some questions that we would consider or think about. What kind of conclusions can we draw? Again, remember, this is an observational study. So again, we like to use data to try to help us with these kinds of questions when we're thinking about the chances that something happens versus not happening. And again, think of it, probability, as that long-term frequency.